last class we had seen the definition of PC curves or parametric cubic curves, and we had mentioned that we can get any point P as u times A, where A is the coefficient of the algebraic matrix of the algebraic coefficients, u is the matrix consisting of the power terms, and the same thing can be expressed as u times MB, where B is the standard geometric matrix and M is the matrix of coefficients of the curves. We had seen 4 curves, F1, F2, F3 and F4. Okay, and we also wrote this as F times B. Okay, this is what we had seen yesterday. And if the 4 curves, their shape was like this. Okay, there are 4 blending function curves, and this was for the case of a PC curve where the B matrix, the standard geometric matrix consisting of P0, P1, T0 and T1. Okay. In contrast to this formulation, if we consider any cubic curve, right now we are specifying this as using 4 parameters P0, P1, starting point, end point, starting tangent vector and the ending tangent vector, that is T0 and T1. Instead of that, if we want the curve to pass through 4 points, okay, that means let us say I say this point, this point, this point and this point. Okay, maybe I say that for u equal to u0 equal to u1 equal to u2 and equal to u3, my points are P0, P1, P2 and P3. Okay, let us say this is P0, this I say is P1, this is P2 and this is P3. That means I want to get the equation of a curve which will pass through these 4 points. Okay, that means I am constraining my curve to pass through these 4 points. I want to interpolate between these 4 points using using PC curves, using cubic interpolation. Okay. If I consider the equation of my curve, which is P equal to u times MB, okay, at u equal to u0 I have P0, so this will become P0 is equal to, let us say I will write u0 times MB, okay, where u0 is a matrix obtained from u equal to u0. Okay, that means this is my U matrix, so u0 will be u0 cube, u0 square, u0 and 1. This is u0. Okay, similarly I can write for u1 and I will get P1 is equal to u1 times MB, P2 is equal to u2 times MB and P3 will be equal to u3 times MB. Okay, so I will get these 4 equations for these 4 points P0, P1, P2 and P3. Okay, what I am saying is these 4 points are specified at 4 distinct values of the parameter u. Okay, again I will write these 4 equations in a matrix form and I will say that let us say this matrix P0, P1, P2, P3, let this matrix be equal to multiplied by m multiplied by b. Okay, what I have basically done is I have taken these 4 equations, okay, where u0, u1, u2 and u3 they consist of 4 vectors like this. Okay, so I have taken these 4 equations and written them down as one single equation. Okay, so P0 will be this vector multiplied by MB, P1 will be this vector multiplied by MB, and so on. Okay, so now if P0, P1, P2 and P3 are given and I want to find out this matrix B, okay, all that I need to do is find out the inverse of these two matrices. Okay, let us say if I say this is a matrix capital P, now I will say B will be equal to P pre multiplied by this matrix in the inverse of this matrix. Okay, so let me just write that as this for the time being, inverse, okay, pre multiplied by M inverse. Okay, this is nothing but M inverse multiplied by u1, u2, u3, u4, transpose of that and the inverse of that, okay, multiplied by P. Okay, where u1, u2, u3 and u4 are, sorry, u0, u1, u2 and u3 are these 4 vectors. u0 is like this, u1, u2, u3 are similar vectors. Okay, so we get B will be a matrix which will be given by this expression. So what that basically means is that if I am given the 4 points P0, P1, P2 and P3, I can find out the standard geometric matrix by pre-multiplying it by these two. Okay, and this maybe I can say is equal to a matrix K times P.
E will also be different, isn't it?
Different from?
The earlier P matrix, 4 points. P is below MB.
P is, no, that was not a matrix, that was the small p I was saying, which was equal to m times u times m times b.
That's a point.
That is a point vector. Okay, this capital P is a matrix of 4 points P0, P1, P2, P3. Okay, and M inverse multiplied by this U inverse, I am writing that as K. I am saying B is equal to K times P. Okay, so if I am given this matrix P, that means if I am given these 4 points through which my PC curve has to pass, I can easily get the the B matrix, that is standard geometric matrix. Okay, and my curve is of course defined as UMB, or it is defined as U times A. Okay, so basically this gives us a method of getting either the A matrix or the B matrix or the P matrix, or the P matrix if any of the 3 are given. If I know the A matrix, I can get the B matrix and vice versa, and if I know the P matrix, I can get the B and A and so on. Okay, the only thing is, for getting this matrix K, I need to know u0, u1, u2 and u3. Okay, so if I take a curve like this and I say that it will pass through these 4 points. Okay, this is, let us say, u0, u1, u2 and u3, and I say u0 is equal to 0, u3 is equal to 1, u1 is equal to 1 by 3 and u2 is equal to 2 by 3. I say that these 4 points are equally spaced on the curve. Okay, so in that case the K matrix that we will get, okay, that looks something like this. Okay, this is for the specific case where u0 is 0, u1 is 1 by 3, u2 is 2 by 3 and u3 is 1. Okay, where k is nothing but b is equal to kp and k is equal to m inverse multiplied by u0, u1, u2, u3 transpose inverse. Okay. This is for the specific case where u0, u1, u2 and u3 are equally spaced. Okay. Any questions up to this point? Okay. The next thing that we will see is that the concept of what is called as composite curves. Okay. See, let us say if we have a curve like this, okay, another curve starting from this point and continuing further. Okay. So far we have considered cubic curves. So let us say this is my starting point, this is my end point of that cubic curve. Okay. Now this cubic curve can be controlled through 4 points. But let us say if I want a larger curve and I want to control it through a larger number of points. In that case we can define composite curves. This is the first curve, the second curve which is starting at this point and continuing further. Okay. So these are composite curves. And this is one curve segment in that curve and this is second curve segment in that curve. Okay, so composite curves are basically a set of curves in succession. Okay, when the question that comes up is, in the case of composite curve at this point, what kind of continuity do we have? Okay, because let us say this is also a cubic curve like this. Okay, this is P0 to P1. This curve let us say defined by Q0 to Q1. Now if I modify this point, if I go and change this point, this curve maybe it will change to something like this. Okay, I am taking a 4-point form of the curve at the moment. Okay, but then at this point the slope of the curve is now possibly going to be different. Okay, so at this point continuity between this curve and this curve might get disturbed. Okay, so the first thing we see is what type of continuity do we get at these curve segments. Okay, so if we consider the first type of continuity that we define is what is called a C0 continuity. Okay. In C0 continuity, okay, we say that the curves have a common endpoint. Okay, that means at this point the endpoint of the first curve and the starting point of the second curve are the same. Okay. In terms of C1 continuity, we say that the curve will have a common tangent. Okay. Similarly, C2 continuity, okay, it is normally C0, C1, C2. Okay, we normally write C2 as C2 continuity, C1 continuity and C0 continuity. In C2 continuity, it will have common second derivative or common curvature.
This is along with C1.
Yes, yes. C2 means C1 and C0 have to be there. only then you can talk of a common curvature. Okay, the slopes are not the same, there is no point in talking of curvature. If the endpoint is not the same, there is no point in talking of the tangent. Okay. So, in this case the points are the same, in this case the derivatives are the same, and in this case the second derivatives are the same. Okay. Similarly, we can define a general kth order continuity. Okay. Well, let us say Ck, we will say that the kth derivatives, they are the same. Okay. So, if you have any two curves, let us say this is if I say that these two curves have a C0 continuity at the common endpoint, that only means that the endpoint is the same, but in terms of slope there can be discontinuity. Okay, if I say that they have a C1 continuity, the tangent vectors would be the same or will be in the same direction. Okay, if I say they have a C2 continuity, the curvature will also be the same at that point. And if I have two curves which have the same tangent vector, let us say, then let us say this curve is defined through these 4 points, this point, and these two are giving the slopes. That means this is the slope at this point and this is the slope here. Okay. So, now if I want to ensure C1 continuity at this point, even if I change P0, my C1 continuity at this point is going to remain unchanged. Okay. If I consider the geometric form of this curve, that will consist of P0, P1, T0 and T1. Okay. This is the definition for this first curve, B matrix for the first curve. Okay. This vector is T1, this vector is T0. So, even if I change P0 and T0, my continuity at this point does not get changed. Well, the tangent at this point is given by T1, the end point is P1. Okay. So, we need to know that if we have a composite curve, what kind of changes will disturb the continuity and what kind of changes will not disturb the continuity. Okay, but if you are modeling a curve in any application, okay, which consists of a series of such curves, we need to ensure that continuity at the common endpoints is maintained, because we do not want a discontinuous curve in most applications. Okay. So, let us take a simple case where we have two curves and we want to ensure that they have a C1 continuity at the common endpoint. Okay. So, okay, let us say if we have one curve like this. Yeah.
What degree of continuity can you define for a curve defined by 4 points? Till what level?
Till what level? That's a good question.
By 4 points, yes. C3.
If the curve is defined through 4 points, so it's basically a cubic curve. Okay. So, your first derivative, that is a second degree expression. The second derivative is a first degree expression. Okay. Your third derivative is going to be a constant. Okay. So, the third derivative is a constant, and your fourth derivatives is going to be 0. Okay. Now, if you have two curves, if you want to ensure first C1 continuity, the tangent vectors have to be the same. For C2, this has to be the same. For C3 continuity, if I look at this term, This is a constant for both the terms. If I can ensure that these two constants are the same, I will get C3 continuity. And if I get C3 continuity, all higher orders of continuity are always there, because all those derivatives are 0 anyway. Okay, but it doesn't make sense to define that continuity, because all those derivatives are 0. Okay, only up to the third derivative we will get non-zero terms. Okay. So continuity can be defined. You can define even higher orders of continuity. Okay, but once you get the C3 continuity, higher orders of continuity don't make any sense in it. Okay. So now if you consider a set of successive curves, let's consider the case where we have, let's say this is my first curve, and this is another curve, and I want to join these two curves by another PC curve. Okay, so this is curve 1, this let's say I call it as curve 3, and I want to join them by another curve, okay, such that C1 continuity is maintained at both these points. Okay, so this is a PC curve. So let's say its geometric matrix is given by P1 of 0 and P1 of 1 are the starting points and the end points. Okay, for this curve the starting point is P3 of 0 and P3 of 1. Okay, the starting tangent vector is, let's say, P1u at 0 and P1u at 1. So this is a B matrix for the first curve. Okay, the B matrix for the third curve is given by P3 of 0, P3 of 1, P3u at 0 and P3u at 1. This is a B matrix for the third curve. Okay, and if I want to define a PC curve between these two points so that C1 continuity is ensured, the B2 matrix, what will be the starting point for that? P1 of 1 will be the starting point. Okay, so the starting point will be P1 of 1, the end point will be P3 of 0. Okay, so this end point is P3 of 0. The starting tangent vector here, that has to be in line in the same direction as this tangent vector. Okay, so we are saying that, let's say it is some k1 times the ending tangent vector here is P1u at 1. Okay, so this will be P1u at 1. The tangent vector here is P3u at 0. So the, let's say we say some constant times P3u at 0. Yeah.
Continuity satisfied only if the directions are the same.
Yes. I just coming to that. I can have this tangent vector as this tangent vector multiplied by some constant. Okay. The direction of the tangent vector will be the same. So we will say C1 continuity is there. Okay, so the unit tangent vectors have to be the same in that direction.
Since we've got a K1 and K2, we have to define another degree of continuity for summing K1 and K2. Do we have to go down to C2?
No, not depending on the values of K1 and K2, you will get different curves. Okay, so if I change K1 and K2, I will get different set of curves. That means you get a family of curves. Okay, my curve can be like this, or it can be like this, or it can be like this, or maybe it can also be like this. Okay, as long as the tangent at this point is the same. Okay, my first curve can come like this and the second curve can go like this. Okay, so I'll get a family of curves depending on the value of the parameter k1 and k2.
So
Okay.
there are models in which continuity is ensured, C1 continuity.
Yeah.
But even there in FEM there are certain models in which continuity is not ensured.
Yeah, then you don't bother about it, that's all.
But then why do you use those models if there is no if you cannot ensure continuity? What is the use of those models? Like if you, because FEM does use like 12 degree of freedom elements.
Yeah.
In that C1 continuity is not ensured.
See, it basically depends on the application whether you want to have continuity in that case or you don't want to have continuity. Okay. For example, if you can see right now I'm modeling curves, and if I say that I want to model, let's say this is the front of my car. Okay. Purely from an aesthetics point of view, I might say okay, this is one curve, this is second curve, this is third curve, and I want to have C1 continuity purely from aesthetics point of view. Okay. For some other application, I might not need this continuity, then I won't bother. Only when I need this continuity will I go for a formulation like this. Okay. In most cases where one is talking of, let's say, aesthetics, either in situations like this or maybe in a ship hull where you don't want to have extra impact because of the waves and all that, you will like to have some continuity between the successive curves. But if there is an application where you don't need that continuity, you don't bother. Okay. Okay. So in this particular case, if you have two curves and you want to get a curve in between, a cubic curve in between, to ensure that continuity, you can use this formulation and get two parameters k1 and k2, by modifying which you can get your C1 continuous PC curve between these two curves. Okay. Any questions up to this point?
So direction of that opposite curve is not exactly the same.
What do you mean opposite curve? This curve?
When you multiply it by -1, its direction gets changed effectively.
Yeah, so the tangent vector that you are giving, okay,
That is 180 degree out of
it's
phase.
180 degree out of phase.
It's not the same tangent vector.
Unit tangent vector is it's the same on the opposite direction. Okay, so depending on this parameter k1, to give it negative values, you can get results like that. It's eventually the question of application whether you want to permit that or not. Okay, it all depends on the application you are considering. Okay. Any questions up to this point?
These tangents from the two curves between the same point in 180 degree out of phase will still ensure C1 continuity.
Yeah, mathematically you can say it is it will ensure C1 continuity.
The mod of
Yeah. Okay, because even if you are giving it a negative direction, you can mathematically say that. But whether the application accepts that or not is a different issue. Okay. Now
for any n derivative.
for any derivative. Okay. Now we will go to another type of curves which are called Bezier curves. Okay. See, so far when we said that we are talking of a 4-point form of a curve, our cubic curve was passing through these points like this. Okay, as we are doing an interpolation between these points. Now we will define a curve which does not pass through these points, but is only an approximation amongst these points. Okay, so we say that it is an approximating curve and not an interpolating curve. Okay, the curve will look like this. Okay, these points, let's say P1, P2, P3 and P4. These points are called control points. Okay, and this curve is an approximating curve and not a interpolating curve. It's an approximating curve, not an interpolating curve. Any point on this will only be approximated by these 4 points. Okay, this curve will never pass through any of these points except the endpoints,
Least square.
except maybe the endpoints. Yeah, again?
Then the least square method.
No.
No. that is a different kind of curve. We will define Bezier curves which will have a different definition. We will give the definition for that. Okay, that is one way of approximating. We are not doing that right now. Okay, I will give a definition for that. Okay, the basic need for or basic properties that are needed from these curves. Okay, the first major property is, let's say we say that the curve should start and end at the first and the last points, okay, at P0 and Pn. Now, right now I mentioned P1, P2, P3, P4, but typically this curve need not be just a cubic curve. It can be a higher degree curve. It can have a degree n. And the degree is n. For defining an n degree curve, we will have to have n plus 1 points. Okay, so the n plus 1 points will be ranging from P0 to Pn. Okay, this is my point P0 and this is my point Pn. Okay, and what we say is that we would like the curve to start from P0 and end at Pn. Okay, we want to define a curve which will go like this. It will be approximated by all these points, and it will go from the starting point to the first control point to the last control point. Okay, we do not want it to pass through any of these points. The idea is that if we have a curve like this, and I move this point from here to this point, to this place, my point I move from here to here, my curve might get modified somewhat like this. Okay, but I do not want my curve to pass through all these points.
Each of the points sort of pulls the curve.
Yes, each of the points will sort of pull it towards itself. Okay, and
What is the relation exactly?
I'll just define the mathematical relation. Okay,
But this curve would be of very low degree than actual curve which can be made to pass.
what do you mean low degree?
A lower degree of the, say if you have 6 points, so we can have a curve of 5 degree passing which can be made to pass through in 6 points.
Yeah, so this
This curve
curve,
would be of much lower degree.
no, this curve will be a degree curve. If I have 100 points, it will be a curve of degree 99.
It would be of that order
Yes.
only.
So this curve will be of same degree as the number of points minus 1. Okay, that is for Bezier curves. But in general, these type of curves do not have that property. Okay, we will see other kinds of curves which do not have that property also. Okay, so if we have a set of points, the first property is my curve should start from here and end at the last point. Okay, this is only what we desire from the point of view of application. Okay, so the starting point should be P0 and the ending point should be Pn. Okay, the other property that we desire from these curves is that slope at P0 should be P0 P1. Okay, that means at this point the slope should be given by this vector. Okay, and at this point the slope should be given by this vector. Okay, I haven't drawn it properly, but anyway. Okay, so at the starting point the slope should be in this direction, end point the slope should be in this direction. Okay, so it says slope at P0 should be this, and at Pn it should be given by Pn minus 1 Pn. It's the other way around, but okay. Okay, actually at this point the slope, I have again drawn it wrongly. Let's say my point is here, I will draw it here. Okay, this is my curve, this is one point, the second point is here, and the slope is in this direction. So if I consider derivative, my u is changing in that direction. Okay, so this is Pn minus 1, this is Pn. Okay, and Similarly, this will also be okay. So slope at P0 should be this, and Pn should be Pn minus 1 to Pn. Okay. The reason why we need this constraint is that again, if we have composite curves, this is one curve and the next curve is starting from here. It's a set of points like this. So the curve goes like this. At this point, let's say we have ensured C1 continuity. Okay. So at this point, if we have C1 continuity, then I know for sure that the tangent vector here will depend only on Pn and Pn minus 1. Okay. The tangent vector in this curve will depend only on Q0 and Q1. So even if I change any of the other points, my continuity at this point is still ensured. Okay, the basic idea is that if I have a curve which I am using in any application, I want to have as much flexibility in modifying the curve as possible. Okay, so just 1 minute. So at this point, the tangent is in this direction. If I change this point, okay, that means let's say I change it from here to here. The slope at this point will still remain the same. So if I have two curves and I have C1 continuity, that continuity does not get disturbed by changing this point or by changing this point or any of the other points. Okay, you are saying something?
Like in composite curve, we ensure C1 continuity by fixing the Pn minus 1 and Q1 point.
Yes. So we will ensure the C1 continuity here by fixing these 2 points. If they are collinear,
That's C1 continuity.
that's C1 continuity. Okay, so that's a simple way of ensuring C1 continuity.
And we can't modify those points.
We won't modify those points, or if we modify them, we will modify them such that they will remain collinear. Okay, so in order to ensure C1 continuity easily, we give this constraint that at this point the tangent vector should be given by Pn minus 1 to Pn, and at this point the tangent vector should be given by P0 to P1. Okay. The next condition that we give is that the RS derivative at the endpoints should depend on next R points.
Next.
Yeah, I'll just explain what I mean. At this point, if I want to find out the second derivative, that should depend on P0, P1 and P2. Okay, at this point the second derivative should depend on Pn, Pn minus 1 and Pn minus 2. Again for the same reasons. If I want to have C2 continuity, I can modify all the other points without bothering. Okay, and this condition,
Second condition is derivation of the third.
yes, I just mentioning this condition is a superset of this condition. Okay, so if the first derivative at the end point will depend only on the next point, the second derivative will depend on the next 2 points, third derivative will depend on 3 points and so on. Okay, this is again purely from the point of view of easy manipulation of the curve. Okay, and the next condition that we, or the next property that we want from these curves is that they should be symmetric with respect to u and 1 minus u. Okay, that means if I take these set of points, whether I specify these points in this order or in that order, my curve should remain the same. Okay, whether I give this as the first point and this as the last point or the other way around, my curve should not get changed. Okay, this is another property that we need from these curves, and all these properties are purely from the point of view of easy manipulation, easy definition and so on. Okay, Now, for these type of curves, a number of definitions can satisfy these properties. One of those is what is called as Bernstein polynomials. Okay, where we define a curve as P of u is equal to summation of I going from 0 to n Pi multiplied by Bi comma n of u. Okay, where Bi comma n of u is equal to nci multiplied by u to the power I into 1 minus u to the power n minus I. Okay. So if you have a set of control points like this is my point P0, this is my point Pn, and we get a curve between these points like this. What we are basically saying is that the coordinates of any point P are given by the sum of the Pi into Bin terms, where Bin is the weightage given to the point I. Okay, so to each of these endpoints will give them separate weightage. Okay, and that weightage is given by this expression. Okay, and u is varying from 0 to 1. Okay, at this point we will say u is equal to 0, and this point we will say u is equal to 1. And these Bins are the weightages given to each of these distinct points. Okay, and these are called the Bernstein polynomials, and this definition is the definition given to Bezier curves. Okay. So let's take a simple case for third degree curves. Okay. So if you consider third degree Bezier curves, okay, for these third degree Bezier curves, n is equal to 3, total number of points are 4, okay, P0, P1, P2 and P3, and we will say P of u equal to, I'll first write the same expression, sigma Pi Bin of u. For P0 we will say this will be P0. Now this term for n equal to 3, I equal to 0, we will get 3C0 multiplied by u to the power 0 into 1 minus u cube. So this will be 1 minus u whole cube, okay, plus coefficient of P1, n equal to 3, I equal to 1. So NCI will be 3, u into 1 minus u square. Okay, I is 1, n is 3. So I'll get 3u into 1 minus u squared multiplied by P1 plus the next term will be 3u squared into 1 minus u into P2 plus u cube into P3. Okay, so this will be a simple equation for a third degree Bezier curve. Okay, where P0, P1, P2 and P3 are the 4 control points. And again, maybe we can write this as F0 P0 plus F1 P1 plus F2 P2 plus F3 P3, where F0, F1, F2 and F3 are the 4 blending functions. Okay. and in this case if you plot the blending functions, okay, the blending functions this is u equal to 0, this is u equal to 1, okay. This is the blending function f0. F0 is 1 minus u whole cube. So u equal to 0 it is 1, u equal to 1 it is 0, and it's a cubic variation. Okay. So this is 1 and this is 0. Okay. Similarly, if I take f3, f3 is u cube. Okay. So f3 would look like this. Okay, and f1 is 3u into 1 minus u square. So f1 looks something like this, and f2 would look something like this. Okay, this is f1, this is f2, and this is f3. Okay, so by looking at this, one can make out that all these 4 blending functions, okay, if I consider f0 and f3, they are symmetric with respect to u and 1 minus u. Okay, if I change u to 1 minus u, f0 will become f3 and f3 will become f0, and f1 will become f2 and f2 will become f1. Okay, that means instead of specifying points in the order of p0, p1, p2 and p3, I specify this to be the first point and this to be the last point, I will still get the same curve. Okay, one can make that out by looking at these blending functions. Okay, instead of n equal to 3, if I take n equal to 4, okay, that means if I take 5 points, then I will get 5 blending functions and my curve will be of degree 4. It will be a biquadratic curve. Okay, this way one can get higher order curves, higher order Bezier curves by using this formulation. Okay, we can get a simple second degree curve. Okay, this is a third degree curve, a simple second degree curve. That means where we have only 3 control points. Okay, where n is equal to 2 and 3 control points. We will get P of u will be 1 minus u whole squared times P naught plus 2u into 1 minus u times P0 times P1 plus u square times P2. This is for a simple second degree curve, and similarly we can get higher degree curves. Any questions up to this point?
Why do we use Bezier?
Why do we use Bezier curves? Okay, the first thing is to get higher degree curves, because in PC curves you are getting only curves up to third degree.
Specify more points, you can get more. Specify more points, even in, like, if you say you specify more points, then specify that.
But that you will have to take a higher degree curve in that case. It won't be a cubic curve. Okay, you have to take higher degree curves. The other reason is, in this you get a better control. Okay, for example, if you have a lot of points like this, and you say the curve should pass through all these points, okay, you will get a very complicated shape of the curve, something like this. Okay, in applications you might like to approximate between these points. Okay, these curves have certain other properties which we will be covering in the next class. Okay, the outer limits of this curve are bounded. It can't go beyond a certain limit. Okay, it will always remain within a closed polygon. Okay, for example, a curve like this can go, let's say these points are positioned wrongly, the curve can go like this. Okay, because the curve has to pass through all those points. That doesn't happen in the case of Bezier curves. In the case of Bezier curves, I am drawing the Bezier curves for the same points, it has to remain within a certain area. Okay, so the curve will probably look something like this. Okay, or it might go within it, but it will remain within a closed polygon. So it has some properties. We'll see some of those properties in the next class. Okay, but in order to get those properties, these curves are defined. And then we'll see how these curves are further modified to get maybe B-spline curves where some additional properties are needed. Okay, we'll go into that in the next class. Any other questions? Okay, in that case I'll stop here now. In the next class we'll see some more properties of these types of curves and then go on to B-spline curves.